we continue our discussion on the dq0 transformation on the flux equations of a synchronous machine. Recall that the dq0 transformation is a time variant transformation, and the basic reason why we actually go for dq transformation is to get a set of time invariant equations as far as the flux relationships are concerned. In the previous lecture, we began transforming even the differential equation, that is the Faraday's laws applied to the flux of the machine, and we noticed that there were, whenever we apply a time variant transformation in the flux equations in the new variables, we do get what is known as a speed EMF term. We will just recap what we have done first before we proceed further in this lecture. So, today's lecture is, we continue to see the implications of the dq0 transformation on the machine equations. Now, recall that the dq0 transformation essentially transforms any a, b, c variables, the phase variables a, b, c, using a transformation matrix C p into f d, f q and f 0, which are known as the dq0 variables. C p is a function of theta. Theta is of course the electrical angle, which we have discussed before. Similarly, of course, f d, f q and f 0 are equal to C p inverse of f a, f b, f c. Okay. So, we assume of course, C p inverse does exist. In fact, we can verify that it does exist. Remember that by doing a transformation, we are just we are going to reformulate the equations in the new variables. Okay. So, we are not writing any fundamentally new physical equations, but we are just reformulating the existing, we will be reformulating the existing flux relationships as well as the flux differential equations in the new variables. Okay. So, once we can do the analysis in the dq0 variables, which is presumably going to be simpler, after we do the analysis, we can transform back to the ABC reference frame using this transformation. Okay. So, that is the basic idea of the transformation. Now, C p of course is this. These k d, k q and k 0 are non-zero constants, 3 non-zero constants, which are used in the transformation. Now, the reason why I have not put any numerical value onto this k d and k q and k 0 is that it is not essential to the values of k d, k q and k 0 can be arbitrary, but non-zero. If there is 0, of course, you will not get C p inverse. Okay, C p inverse will not exist. So, k d, k q, k 0 are in fact non-zero constants. Okay. And whatever be their value, as long they are not 0, they satisfy our purpose of trying to convert the time variant flux relationships into time invariant flux relationships in the dq0 variables. C p inverse in fact looks like C p transpose. In fact, if you look at the structure, you will see that you have got cos theta minus 2 pi by 3 and cos theta plus 2 pi by 3 here. These constants k 1, k 2 and k 3 are related to k d by this relationship. K 1 is equal to 2 by 3 times k d, k 2 is equal to 2 by 3 times k q and k 0 is equal to 1 upon 3 times k 0. So, this is basically the inverse. You can just verify this of course, at leisure by multiplying C p with C p inverse and just verifying that it does turn out to be an identity matrix, which will of course verify that C p inverse is indeed the inverse as I have written it down here. Okay. Now, the basic idea here is to convert the flux equations. Okay. So, what we will do is try to convert the ABC, the psi s, remember, is nothing but psi a, psi b and psi c, and psi r of course is psi f, psi h, psi g and psi k. Psi dq, so what we do is try to change the variables a, b, c to dq0. Of course, psi r we will keep unchanged. So, the transformation, if you look at it, is C p, this submatrix C p, the submatrix of this larger matrix has got this element as C p. This is a 3 by 4 null matrix, this is 4 by into 3 null matrix, and this is an identity matrix which is 4 into 4. Okay. So, what I will do is I will apply the transformation, okay, to these variables. Remember that the flux current relationship is psi s is equal to LSS of theta, LSR of theta, okay, LSS of theta into IS into LSR of theta into IR, and similarly psi r is expressed in this fashion. Okay. Now, if I call this the L matrix, I will call this L. Okay. It's easy to see that psi, if you try to reformulate this particular equation, we are just reformulating it in the new variables. Okay. So, psi dq0 psi r will be this, okay, into L. L is nothing but this matrix. Okay. Remember, of course, these are sub matrices. So, this into L into this transformation into I dq0 in IR. Now, the good thing which we saw in the last lecture was when we work out this, okay, we did work out one particular term in this L matrix, but I encourage you to actually try out to evaluate the complete L matrix. Okay. The complete L matrix, if one evaluates, one will find that of course, this you get this new relationship where this dash, I have called this LSS dash, LSR dash, LSS, RS dash and LRR. LRR of course remains unchanged. So, LSS dash, so this should be LSS dash is nothing but, it turns out, is a diagonal matrix. That is an interesting thing. It is a diagonal matrix, okay, where LD, LQ and L0 are not functions of theta. So, that is the basic beauty of this transformation, is that the relationships in the dq0 variables are in fact, the flux current relationship in the dq0 variables are in fact independent of theta. Not only that, as you see LD, for example, if you just expand this, you will find that psi d is equal to LD into ID plus 0 into IQ plus 0 into I0. So, there seems to be a decoupling in the flux relationships. That is also an interesting thing which happens because of the fact that this is diagonal. In fact, LSR dash is this MAF by KD, MAH by KD 0 0 0 0, MAG by KQ, this is wrongly written. So, I will write this AKQ and MAH by KQ, okay, and the last column of course is the last row is 0. Now, LSR dash is equal to LRS dash only if this is true. So, it is not true in general. See, remember LSR was equal to LRS transpose, okay, but this is true only if we choose KD and KQ such that they satisfy this relationship. KD square is 2 by 3 and KQ square is equal to also 2 by 3. Okay. Now, what you see here is, of course, there is a complete decoupling between what are known as the d axis coils. What are the d axis coils? F, okay, H and the stator coil which is transformed into the dq frame. Okay. So, if you look at this will be F, H and D on this and G, K and Q here on the Q axis. So, the basic idea here is that basic thing which comes out is that the fluxes in the coils on the D axis, including this, this fictitious coil, we will call it the D axis coil, is not dependent on the Q axis currents. Now, that is a very interesting thing. In fact, it is tempting to think that this transformation, what it essentially has done is represented the 3 stationary stator coils in the ABC frame of reference. Okay. It has kind of converted these 3 stationary ABC coils into 2 rotating DQ coils, okay, which are also rotating at this angular frequency omega. Okay. This is tempting, but as we shall see soon, when we write down Faraday's equation, we will see that the EMFs induced in this, okay, will be dependent on the fluxes caused in this axis. So, we should remember that although this gives a nice picture of the decoupling of the fluxes and the currents in the D and Q axis, the EMF equations of course have a coupling. Okay. So, what do I mean by that? We did this in the last class. We have seen that d psi by dt, psi of course is nothing but psi s and psi r, is equal to minus of r I minus of V. This is what basically our flux equations were, which we did in about 2 classes back. R of course is a diagonal matrix which has submatrix R s and R r. Okay, R s and R r. R r of course are it's a diagonal matrix containing the resistances of the F, G, H and K coils. Okay. I of course is I s and I r, V is nothing but V s and V r. So, what you have, if you just take out the psi s equations, you will have d psi s by dt is equal to minus R s I s minus V s. Of course, psi s, the subscript s actually denotes. So, psi s is nothing but actually psi a, psi b and psi c, and similarly I s and V s are I a, I b, I c and V a, V b, V c. Okay. Now, if you look at this equation, we can substitute psi a, psi b, psi c as nothing but C p into psi dq0. So, our equations in fact become this. Okay. So, I have just rewritten the equations, these equations, these ones. Okay. I have rewritten it like this, and the rewritten equation I have substituted for I s, which is nothing but I a, I b, I c. I have substituted it by dq0 variables. So, V s is nothing but C p into V dq0. Okay. So, if you recall our discussion in the previous class, I had asked what is C p psi dq0. In fact, it is minus of C p, minus of this is nothing but minus of C p, this is applying the chain rule, plus this extra term. Remember that C p, unlike some of the transformations we did in the first few lectures of this course, C p is in fact a function of theta. Theta in a synchronous machine is a function of time. It can't be considered even under steady state conditions. You will find that theta is in fact varying continuously. Okay. So, d C p by dt in fact has to be evaluated. We have to apply chain rule. Okay. So, what we will get is this is in fact having 2 terms. Okay. So, your flux relationship, so I will just this has been rewritten again. This particular term d C p by dt can be written as d C p by d theta into d theta by dt. Okay. So, this extra term, as we discussed in the previous class, comes out because of being mathematically consistent while applying the transformation of variables. Okay. This extra term in fact denotes, what we this rate of change of flux of course is common with the ABC equations, but we have got this extra what is known as PDMF term. Okay. So, if you look at this dCp by dt, if we actually evaluate it, in fact, so we carry on forth from last time, dCp by dt d theta, okay, is equal to, it is easy to see this, you take the derivative of the transformation. So, we will get minus k d sin theta k q cos theta, and of course, k 0 when you take the derivative you will get 0. Okay. So, I will write 0 here, and you will have minus k d sin theta minus 2 pi by 3. Difficult to fit it in a paper, but we will just try to do that. K q into cos theta minus 2 pi by 3, and this will be sorry, this is, yeah. So, minus k d sin theta plus 2 pi by 3, and this term here is k q cos theta plus 2 pi by 3. Okay. So, this is basically what we have. I will just read out this term, it may not be very clear here. It is k q cos theta plus 2 pi by 3, and this is of course a distinct term here. Okay. Now, it is very easy to see, I mean it is not too difficult. You know how what Cp looks like? The Cp looks like this. Okay. Sorry, this is Cp inverse, I am sorry. Cp looks like this. So, it is very by inspection you can really make out that this is nothing but Cp into a matrix P1, where P1 is nothing but 0 k q by k d 0 minus k d by k q 0 0, and this is 0 0 0. So, what I have, so let me just repeat, d Cp by dt d theta is equal to Cp times P1, okay, where P1 is this. Okay. So, our final equations, flux equations come out to be minus of Cp d psi dq0 by dt minus d theta by dt. So, I will just call this theta dot Cp P1 psi dq0 minus Rs into Cp I dq0 is nothing but Cp into V dq0. Okay. So, your flux equation becomes in fact, I will just pre-multiply both sides by Cp inverse, you will get minus d psi dq0 by dt minus theta dot into P1 into psi dq0 minus Rs, of course, remember is a diagonal matrix containing Ra, Rb and Rc. Of course, if all the coils are identical, I can just say Ra into I dq0 is equal to V dq0. Which leads us to, if I really write this down separately, because it sometimes is not very evident what we are getting unless we write down all the equations separately. So, what I will do is I will write down the dq0 equations separately. Okay. So, the dq0 equations separately turn out to be minus d psi d by dt minus d theta by dt, in fact, or theta dot is nothing but, it is nothing but omega, okay, angular frequency, okay, electrical angular frequency, and this is k q by k d psi q minus R A I d is equal to V d minus d psi d q by d t plus omega k d by k q psi d minus R A I q is equal to V q and minus d psi 0 by d t minus R A I 0 is equal to V 0, okay, where omega is equal to d theta by dt or d theta dot. Okay. So, if it is not clear, I am just spanning this a bit. Okay. Now, one interesting thing which you should see here is that there is what I mentioned some time back, the speed EMF terms. In fact, although we saw that there is complete decoupling between the D and Q axis. So, recall we had a complete decoupling between the D and Q axis, if you recall this equation or the flux equations. So, in fact, we had I mentioned some time back that psi d is dependent on I d, I f and I h, but it is not dependent on I q, I 0 or I g and I k. It is not dependent on the q axis coil. So, the flux current relationships, there is a complete decoupling between the D and the q axis coils. Okay. So, I call this the D axis coil. So, the fluxes in the D axis coil are not dependent on the q axis currents, okay. None of the currents, but importantly, when you look at the flux equation, there are speed EMF terms. So, the flux Faraday's law, when you apply it to psi d, you have to put this extra term which comes because of applying the correct mathematics to the transformed equations. Okay. So, although sometimes it is tempting to start from a kind of a physical model of rotating windings, okay, when we come to obtaining the flux equations in the D coil or the flux equations in the Q coil, remember that there are speed EMFs in the D coil, okay, due to the flux in the Q axis. This cannot be explained by just starting off from this model. So, one of the things which you should keep in mind is that it is a good idea, as I mentioned in the previous class, to first work out the mathematics. The correct mathematics gives you these equations where there are extra speed EMF terms. The speed EMF terms come because we apply the derivative to the time varying transformation as well. These are the correct equations. Okay. So, please remember that there is coupling coming between the D and Q axis coils because of these extra what I call as speed EMF terms. Okay. Now, these are as far as the stator equations are concerned. The rotor equations, of course, we know and d psi g by dt is equal to plus r g I g is equal to 0. So, just remember these are the remaining equations. In fact, if you know the flux and current relationships and these equations relating to the EMFs, the rotor flux equations in the D axis and in the Q axis, we in fact have got the complete flux description. Okay. So, if I know, of course, I should the relationship psi dq0 psi r, I know this relationship as well. Okay, dq0 and I r, okay, and this is nothing but L S S dash L S R dash L R S dash and L R R. So, we have in fact got a complete picture of the system. In fact, you can substitute for I g, I k, I f, I h as well as I dq0 by psi dq0 and psi r using this relationship, and you will get finally things in the state space form. I will just do it on a separate sheet. So, you will get, you can of course write it as psi dot is equal to some A matrix into psi plus B into V. Okay, so, we can get it in this form where psi is nothing but psi dq0 and psi r. Okay. This A is in fact does not have time coming in explicitly. Okay. You do not have time or theta coming in explicitly. Of course, A does contain omega. Remember that because of the fact that the equations of flux have the speed EMF term, A is a function of omega. So, but if omega is a constant, then this A becomes linear, this particular equation becomes linear time invariant. Okay. So, that is the beauty of applying the dq0 transformation. If you have constant speed, of course, this becomes a linear time variant equation. There is no explicit dependence on theta, which itself changes with time. Okay. So, this is one of the main important things which really comes out of applying the dq transformation. Now, in general, of course, whenever you have a linear time variant system, it is not obvious that by transforming it in a certain way, you will get a linear time invariant system. Okay. It turns out that the machine equations have a special structure which permit the use of this transformation Cp, okay, which make the system time invariant. Okay. Now, one of the things we have not discussed now, we will shortly again discuss it. This feature of making the equations of flux equations of a machine time invariant is not dependent on the specific values of Kd, Kq and Ak0. It could be absolutely arbitrary choice. Okay. Of course, Kd, Kq, K0 should not be 0, none of them should be 0. Okay. So, there is some flexibility in the choice of Kd, Kq, K0. Okay. Now, before we go on to discussing this particular point again, let us just look at what happens to the torque equations. Now, if you look at the torque equation, just recall what was the equation for torque. If you recall what we did some time back, I will just show you the equations first. So, you can recall what we have done. This was the torque equation in the previous lecture, where T e is nothing but the minus of the partial derivative co-energy with respect to the mechanical position. Okay. Torque T e of course, is in this direction, theta is measured in this, theta and theta m are both measured in this direction, the anticlockwise direction here. The co-energy is expressed as a function of currents. Okay. So, you have got this particular formula, and of course, eventually we did get this. So, T e, which is the electrical torque, is nothing but minus of p by 2 into p is the number of poles into d by derivative, partial derivative of co-energy with respect to theta, which is the electrical angle. Okay. So, we call of course T dash as this. So, T dash turns out to be this. Okay. So, this is what our equations are. I basically took out the derivative, partial derivative of co-energy with respect to this. So, now if I want to get this expression for torque T e dash, okay, remember T e, the actual torque is actually minus p by 2 times this. Okay. So, we will have T e is equal to T e dash. Okay. The actual torque, remember, is p by 2 minus p by 2 times T e dash. Okay. So, T e dash is nothing but 2 by p times T e. Okay. Half. So, I substitute here. So, I have got I s transpose here. So, I will have to write I s, remember, is I a, I b, I c. So, I can write this as I d Q0 transpose into Cp transpose, okay, into the partial derivative of LSS with respect to theta. LSS, remember, is the submatrix of the original L matrix into, okay, there isn't much space here. So, I will just okay, we can write it here, I guess, I dq0. Okay. Is here is Cp into I dq0. Inadvertently, we have just written I dq0. Remember, I dq0 is a row, rather a column ID, IQ and I0. Okay. So, this is just a neat way of writing it, plus, okay, plus, in fact, this is 2 times I dq0 transpose Cp transpose d LSR by d theta into IR. Okay. The closing of the curly bracket. Okay. So, what we get is this. You can just work out, we have already about 2 lectures back, we took out what LSS is actually. So, I will just write down what d LSS by d theta is nothing but minus of 2 L A 2, this is the time varying part or the theta varying part, into, okay, sine of 2 theta, sine of 2 theta minus 2 pi by 3, sine of 2 theta plus 2 pi by 3, sine of 2 theta minus 2 pi by 3, sine of 2 theta plus 2 pi by 3, and here sine 2 theta, and of course, this will be, I will just, since it may not be very clear, I will just read it out, sine of 2 theta plus 2 pi by 3 is not very clear here. So, maybe we will just write it down again. I will just write, so d LSS by d theta is equal to minus 2 LAA 2 sine of theta, sine of 2 theta, sine of this is this LSS by L theta. Okay. D LSR by dt will partition into d LSR d by d theta and d LSR q by d theta. So, that turns out to be MAF sin theta minus MAH sin theta Okay. So, a bit of bookkeeping is required, but as we shall see soon, then finally what we get as the torque expression after using these formulae is quite neat. So, this is what d, if we know d LSR is this. Okay. So, we have found out these sub matrices which I mentioned some time back. Okay. Now, you can see that d LSS by d theta into Cp is nothing but minus of 3 LAA 2 into Cp into P2, where P2 is zero Kq by Kd, 0 Kd by Kq, 0 0 and 0 0 0. So, you can rewrite this. So, if you look at the structure of d LSS by d theta, if you look at the structure of it, okay, you can write it as in this fashion. Okay. Therefore, and further you will find that Cp transpose of d LSR by d theta is nothing but, in fact, it gets stripped of all the thetas eventually, 0, 0, 3 by 2 Kd MAG, 3 by 2 Kd MAK, and this becomes minus 3 by 2 MAF, minus 3 by 2, sorry, there is a KQ here. So, there is a KQ, KQ MAH 0 0, 0 0 0 and 0. So, a bit complicated, but this is how it comes out to be. Okay. You can just verify this. So, eventually we get, I'll just write down the torque equation. Te comes out to be 3 by 2 times Kd Kq into Iq into MAF by Kd If plus MAH by Kd IH plus 3 by 2 LAA2 ID. So, I close this bracket, then continue, minus ID times MAG by KQ IG plus MAK by KQ IK minus 3 by 2 times LAA2 IQ, close this bracket and close this curly bracket here. So, this is the expression for torque, okay. But we know that, so I will just partition this here. We know that psi d is nothing but L d I d. This comes out from the flux equation. Psi d is equal to L d I d plus MAF IF by Kd plus MAH by Kd IH, and of course, psi q is nothing but LQ IQ plus MAG by KQ IG plus MAK by KQ IK. So, what do we understand from this? If you look at these equations, look at this and you look at this. Okay. So, one can directly infer from this that T E is nothing but 3 by 2 times K D K Q. Again, we will put a curly bracket here. I Q into psi D minus L D minus L A 2. We will rewrite this again. You can rewrite T E is equal to 3 into K D into K Q into a curly bracket here into I Q into, we will put a square bracket here, psi D minus L D minus 3 by 2 L A 2 into I D, and I close the square bracket, minus I D into psi q minus L q plus 3 by 2 L A 2 into I q. So, I close this bracket and I close this bracket. Okay. So, if you from this, it is very easy to see, you can cancel off this term here, you will get really, after all the manipulations, finally it yields 3 by 2 times K D K Q psi D I Q minus psi q I D. In fact, this is a small correction here. So, I should be calling this T E dash, okay, this T E dash. So, this is nothing but T E dash, and T E dash is this. Okay. So, what we have here is basically a very neat expression, which is again devoid of any of the thetas. Okay. They are all in terms of d and q variables only. Okay. So, that is one interesting thing. So, our equations are turning out to be extremely neat. Now, in fact, if you write down the equations in dq variables, you will find that your equations no longer will have theta explicitly appearing in them. They are much easier to handle. The flux current relationship is brings out a decoupling between the d and q axis fluxes and currents. The flux differential equations, of course, bring out a coupling between the d and q axis fluxes. There is a coupling. Okay. We now get the torque equation. Remember what the torque equation was? If you recall where we were some time back, this. So, T E dash we have actually found out right now, okay, which I said was a function of theta, but of course, because we applied the dq transformations, it turns out that it is not explicitly coming, the theta does not come out explicitly if you express T E dash in terms of the dq variables. Okay. So, it is a very interesting and very neat expression we get for torque. Okay. Now, one thing about the choice, the last topic in this particular lecture, what about the choice of Kd and Kq? We saw of course that if we put Kd square is equal to 2 by 3 and Kq square is equal to 2 by 3, one interesting thing happens, that is LSR dash becomes equal to LRS dash transpose. Okay. Also, if in fact we saw some time back that when we take out Cp inverse, it is in terms, it has got elements K1, K2 and K3, where K1 is nothing but 2 by 3 times Kd and K2 is 2 by 3 times Kq. In fact, Kq is in the denominator and Kd is also in the denominator, and K3 is equal to 1 upon 3 K0. So, these are the coefficients of the sines and cosines in the Cp inverse matrix. If you look at these relationships, it appears that it is not a bad idea to choose Kd equal to Kq is equal to root 2 by 3. Okay. So, that is an interesting and important point here. Of course, there is absolute freedom in choice of Kd and Kq insofar as our main objective of getting a time invariant set of equations. Remember that Kd, Kq do appear in the flux current relationship as well as the flux differential equations, as well as in the torque expression here. Okay. Sorry, this should be Kq, but the fact remains that although Kd, Kq do appear, theta does not appear. So, whatever be the value of Kd and Kq, as long as they are non-zero, we do end up with what we have set out to do, that is get a neat set of equations which are invariant with respect to theta. Okay. So, if we choose Kd and Kq root 2 by, it is a very special choice. It will lead us to LSR dash being equal to LRS dash transpose, which is convenient, it is very convenient. Okay. Also, we will find that Cp inverse will be equal to Cp transpose. So, it is of course, it is easy to remember, that could be one advantage of choosing Kd and Kq in this fashion. So, it is easy to remember that Cp inverse is equal to Cp transpose, but let me repeat, Kd and Kq could be arbitrary insofar our main objective of getting time invariant equations is concerned. Okay. So, let me just summarize, but before I do that, it is Kd is equal to Kq is equal to root 2 by 3 is a kind of a it is a special choice, and that is the choice which I will really follow in this particular course. It is in fact the same choice is used in K.R. Padiyar's book. In fact, if you look at the other literature or many industry papers, they follow a convention Kd is equal to 1 and Kq is equal to minus 1. So, they follow this choice. Okay. In fact, of course, I did not talk about K0. K0, if I want this to be true, in fact, I should have told you before, you have to choose K0 is equal to 1 by root 3. Okay. So, K0 also gets defined if I want to have this to be true. Okay. So, just remember this again, that many industry papers as well as in books by Kundur and many other books, they follow the convention Kd is equal to 1 and Kq is equal to minus 1. In this particular course, I shall follow Padiyar's convention, which is, or the IEEE convention actually, which is Kd is equal to Kq is equal to root 2 by 3, because it gets us some benefits. Okay. In fact, you will notice that in this torque expression, if I choose k d and k q as root 2 by 3, this this whole coefficient becomes equal to 1. So, I do not have to remember these coefficients, because this if I put k d is equal to root 2 by 3 and k q is equal to root 2 by 3, this coefficient effectively becomes 1. So, there are certain advantages in choosing this, but as I mentioned back, the choice is arbitrary. It does not hamper our effort to get a time invariant set of equations. Okay. Of course, the question then arises, if we have got industry papers or books which follow this convention. Okay, I will call this people who follow this convention as using a transformation CP1, and we in fact apply a transformation CP where k d and k q are root 2 by 3. Okay. In such a case, one can transform the equations which they have used, the people who are using this set of values of k d and k q, by again a kind of matrix T k. So, I can actually, the variables which they have defined are different from my variables, because the coefficients k d k q have been chosen by them to be 1 and -1, and we are going to choose root 2 by 3. Okay. So, whenever I am going to use their equations and I get answers with their variables, I would need to use this transformation matrix T k, okay, to transfer from their variables to my variables. Okay. So, I leave this as an exercise for you to find out what this T k is. It is a very simple constant matrix. Okay. So, to summarize this particular lecture, what we have done is finally obtained the equations of the synchronous machine in the dq frame of reference. Okay. And the equations are neat in the sense that they are not functions of theta. In fact, you can if in fact the speed of a machine is constant, that is d theta by dt is equal to constant, the flux equations, the flux differential equations are linear time invariant equations. Of course, if speed is not constant, in fact, in general it need not be a constant, you have a coupling between the mechanical equations and the flux equations, flux differential equations. Okay. In fact, that coupling is non-linear. Remember, the torque is psi d I q minus psi q I d. Okay. So, there is a product terms there. Also, there is a product when you are talking about the speed EMF terms in the flux differential equation, therein also there is a product. Okay. So, the mechanical equations and the flux equations are in fact coupled in a non-linear fashion. Okay. But the flux equations themselves for a constant speed are in fact time linear and time invariant. That makes at least some of our analysis much simpler. Okay. So, now we move on to trying to interpret the equations which have come, correlate it with parameters obtained by measurement, and thereafter the most important thing of course in this course is to draw inferences from what equations we have got, okay, and correlate them to actual power system behavior.